So today we're going to look at the first part of 2-6. We're only going to focus on identifying the domain and range of parent functions and identifying the domain from a function rule. These two right here we'll get to on part 2. So let's go ahead and look at some terms. So undefined, this should be a review that you had from algebra. So an undefined expression has no mathematical meaning. We don't know what it is. For example, if you divide by 0, that's undefined. In other words, if you had 4 divided by 0, and I'm going to use UD for undefined, that's not possible. You can't take a group of 4 and divide it into no groups. At the very least, you have one group of 4. You can, however, take 0 and divide it by 4. 0 divided by 4 would be as if you had $0 and you wanted to split that amongst 4 groups. Each group gets 0. Here you can look at this as having $4 that you're going to split into no groups. You can't take $4 and to split it into no groups because you have at least one group of $4. So that's an example of something that is undefined. Another example would be taking the square root of a negative number. So you might be looking at the square root of -4. We cannot take the square root of -4 because there is no number times itself that gives you -4. -2 times -2 is +4, so that doesn't give you -4. And 2 times 2 is +4, that doesn't give you -4. So there is no value times itself that gives you a negative number. But we could take odd roots of negative numbers, that's okay. All right, so then the other thing I want to discuss is a function is undefined for numbers outside its domain. So remember, domain are x values. In other words, when we evaluate at these x values, we get an undefined expression. So there are numbers that we can take the square roots of. We just can't take the square root of a negative number. We can take the square root of 0. The square root of 0 is 0. And we can take the square root of positive numbers. So the square root of 4 is 2. So in other words, the domain of the square root of some number is going to be any number 0 and greater. So that means our domain x will be greater than or equal to 0. Any number greater than or equal to 0 you can take a square root of. Here's another example of fractions. So remember, just like we cannot divide by 0 here, that denominator, this x minus 2, cannot be 0. So if I set just the denominator, and this is something that you explored in algebra, if I set that denominator not equal to 0 and solve for x, wouldn't I add 2 to both sides here and here? So wouldn't I end up with x cannot equal 2? So as long as x is anything but 2, it will make this fraction a true fraction. So like if I put 2 in here, 2 minus 2 is 0. 1 divided by 0 is undefined. But any other number, 4 for instance, so 4 minus 2 is 2, so 1 over 2 is a real fraction, 1/2. Or let's do a negative number. -4 minus 2 is -6. 1 over -6 is -1/6. That's a real number, a fraction. So our answer to this one, f of x is equal to 1 over x minus 2 is undefined at x equals 2. It's defined everywhere else, just not at x equals 2. We're going to talk about how that domain looks using set notation. Then the final thing that we're going to talk about today is what is a parent function. There are, I believe, about 12 parent functions that you're going to have to recognize and know what its parent function looks like without having to graph it. The more times you graph these, the more comfortable and familiar you become with them. And so tomorrow on day 2, we're going to actually translate these up, down, right, left. We're going to reflect them, all kinds of stuff. So you have to know your parent function before we start to translate them. And we're going to spend time going to each one of these in detail. So we're going to do a brief overview at first, and then in our successive chapters and sections, we're going to go through all of these different ones individually. So let's talk about this parent function. So a parent function is the simplest form of a function that forms what's called a family of functions. So we're going to put here simplest. And an example would be, let's just take the quadratic function, which you did a lot with in Algebra 1, 2. So each quadratic function, so a quadratic function is y equals x squared, and that's just your parent function. So each quadratic function is a transformation, meaning we've taken the basic parent function and moved it up, down, right, left of the function. And so here comes the parent function, y equals x squared. So that's your basic quadratic function, y equals x squared. Then you're going to do things to that, which we'll talk about as we go along, that's going to create this transformation. An up, down, right, left movement, a reflection over the x-axis, a reflection over the y-axis. You can even reflect over different lines. So the function y equals x squared is the parent function of the whole quadratic family. So a quadratic family, remember, a quadratic function looks like this. It opens up, looks like a U that opens up or down. All right, so that's just one of our parent functions. So let's go ahead and look at and sketch each of these. And you can throw these into your calculator as well to kind of help you sketch them. You should not need your calculator after about the next week. You should start to know these. Some of them I'm not going to explain why the graph is the way it is. Some of them I will, but just know that each of these we will go into a lot more detail later. So for each of these we're going to look at domain and range, and we're going to graph them. And some of them we'll graph specifically and some we'll just do in a general format. All right, so our first family function is going to be called the constant function. So each of these families has a name. So if I mention the name, the constant function or the linear function or the absolute value function, in your brain should pop a picture of what that looks like. So your constant function, you actually have graphed a lot of. So here's an example of what it might be, like y equals 2. A represents just any number. And remember, f of x is always y. So this is either a vertical or horizontal line. So remember, we can figure out what that is by okay, so I'm going to plot 2 on the y-axis because it says y equals 2. And then the only way to cut the y-axis into 2 pieces is using a horizontal line going in this direction. So this is just an example of y equals a. So it's going to be a horizontal line going in this direction, and you can have an infinite number of them going all up and down this y-axis. This is just one example. So I don't really have a parent function per se. So this is one of those odd ones. So your domain, notice that we don't mention anything about our x values. If you look at this, the domain goes from left to right. So there is no break in our domain. If this goes left infinitely, that's negative infinity, and it goes to the right infinitely, that's positive infinity. So in set notation, our domain is negative infinity to positive infinity. And then our range, notice that this says y equals 2. So in this particular case, our range is just 2. Notice that every ordered pair on this line, they all have the same y, 2, and that's our range is our y. So for our parent function, our range is going to be whatever a is, and so it is going to look like brackets a, brackets. Remember, brackets are closed, and that means that the range includes this value, and since there's only one value for the range, it's going to have brackets. All right, so then let's move on to the linear function. This one you are quite familiar with, and this happens to be the equation of y equals x. And if this were in y equals mx plus b, our slope is 1, and there's no plus b, so that means it goes through the origin at 0. So it goes in this direction. I can't draw a straight line, but you could. And the slope of this line is 1, so up 1 to the right 1, up 1 to the right 1, or down 1 to the left 1, down 1 to the left 1. And so that's your parent function. And that whole part of, let's write it down here, the whole thing of having y equals mx plus b, those are where your transformations and your stretches and shrinks are going to occur. This is going to move your graph either up, down, right, left. We're going to find out tomorrow. And then this right here is going to stretch or shrink our graph, either vertically or horizontally. Again, we're going to talk about that tomorrow. Now our domain goes from left to right. So from left, this graph is going down and to the left forever, and it's going up and to the right forever. So our domain has no restrictions. Any x value, I can put any x value into here and it'll give me the same y value. Your x is exactly equal to your y. And so the range is going to be the same thing. Whatever our x is, our y is going to be. So if our x is undefined, meaning it can be anything, then your y can be anything. And if you think about it, your y here, this goes down infinitely, so that's your lowest y direction is down, so that's negative infinity. And it goes up infinitely, which is positive infinity. So your range here for the linear function is also unrestricted, negative infinity to positive infinity. Then we move on to the absolute value function, and we graphed this when we did piecewise functions. And it really is an interesting graph. So if you wanted to plot it, we'll just plot a couple of things so I can prove to you that the graph is what it is. I'm going to do it fairly quickly. So make a 4x4 grid. We're just going to plot some points. So if I substitute in a value for x, the absolute value of this x value is always going to be its positive form. So if I let x be 0, the absolute value of 0 is 0. So it's going to be 0, 0. If x is 1, the absolute value of 1 is 1. So it's going to be 1, 1. And if x is 2, the absolute value of 2 is 2. 3 is 3, and 4 is 4. So it actually looks like this graph right here is the identical graph here. However, when you go to the left side, if I substitute in -1 in here, the absolute value of -1 is +1. So this graph all of a sudden gets reflected up over here. The absolute value of -2 is +2, and -3 is +3, and -4 is +4. So you end up with a graph that looks like this. It looks like a V. And it has this definite bounce right here. That's going to be an important part for you to find when we start to translate this graph. So to find the domain, again, this graph is going to the left and up infinitely, and to the right and up infinitely. So it's left infinite and right infinite. So our domain is unrestricted. There is no value that I can't place in here for x and find the absolute value. There's no possible value of x as long as we use a real number. So our domain is going to be -infinity to +infinity. But our range, we have to start low and go high. The lowest part of the graph we reach is here, and the y value of that point is 0. So our lowest y value starts at 0. And because 0 is a y value in one of the ordered pairs on the graph, it is included. So since 0 is included, we have brackets and then comma. So then we start here at a y value of 0, and we continue up infinitely forever, because this graph is going up to the right and up to left forever. So infinitely up forever is positive infinity. And so what this is saying is that all y values are greater than or equal to 0. And isn't that the case? All y values are all up here, which is greater than or equal to 0. Then we come to the quadratic function. So this is one that you should have spent a lot of time graphing in Algebra 1-2. If you're not sure what the parent function is, I always will substitute in -2, -1, 0, 1, and 2 in for x. And we're just going to square it. Recall that anytime we square a number, positive or negative, we will get a positive value. So again, I'm going to make a 4x4 grid. Okay, and so then let's start plotting some values. So if let's just try -2, because it's my lowest value that I'm going to plug in for x. If I substitute in -2 for x and square it, I get a +4. So -2, +4 puts us up here. Then when you substitute in -1, -1 squared is +1. So we come down to here. The next x value is going to be 0. 0 squared is 0, so we get 0, 0. And then the next value plug in is 1. 1 squared is 1. So now you see it bouncing back up. This kind of looks a little similar to the absolute value graph, but this one has a curve, but it has a lot of similarities. And then 2 squared is 2. I'm sorry, 2 squared is 4. I know math. All right, so then if we connect these values with a curve, not a straight line, because this is definitely a curved graph, there's your parabola. So another word for the quadratic function is a parabola, and it has the identical domain and range as the absolute value function does. Why? Because it goes left infinitely and right infinitely, so there's your -infinity to +infinity. And then the lowest y value starts here at 0 and includes 0 and goes up infinitely forever. So our domain is -infinity, +infinity, and our range goes from 0 to +infinity. Okay, so let's look at our last one on this row, and this is your cubic function. So this one is new to you. You probably haven't graphed this much, if at all. So we are going to have trouble getting this on our graph. So let's just suffice it to say, if I plug in the same values here as I did here, it's going to accelerate a lot faster. In other words, if I put in -2, -2 cubed is -2 times -2 times -2, which is -8. So you can see, we'll try to graph it here. So I'm going to be way far off on my graph here, but if I take -2 and cube it, I get a -8. So -2, -8 is going to put me, I don't know, like way down here somewhere. It's probably further than that, but that's where I'm going to go. And then if I take -1 and cube it, -1 times -1 times -1 is -1. And if I take 0 and cube it, 0 times 0 times 0 is 0. Take 1 and cube it, 1 times 1 times 1 is 1. So if all you graphed were these three values, you would think it's linear, but it's not. It has a curve because it goes from here, and then it's going to go back up. So 2 cubed, 2 times 2 times 2 is 8, so we'd be like, way up here somewhere. And so the connection is going to go, it looks like a little S curve. And basically what's happened is it almost looks similar to this curve right here, although it's stretched a little bit, and then this curve here got reflected over the x-axis and went that way. Now, our domain and range. This graph goes to the left infinitely and down infinitely. It goes to the right infinitely and up infinitely. If you think about it, there is no value for x that I can't cube. I can put any value I want to in for x and cube it, and I'm going to get both positive, negative values for y and 0. So both your domain and your range are -infinity to +infinity. Now these domains and ranges can change when we translate them. So it's not always the same domain and range for every item in a parent function. It depends on what the transformation is. Okay, so let's look at this bottom row. On this bottom row, every one of these parent families have a restriction on the domain, with the exception of the cube root function. That one, there's no exception, but every other one is going to have some sort of a restriction on the graph. So let's go ahead and look at these. So the square root function, we're going to make a 4 by 4. All right, so this is essentially, and you need to add this onto here, that's the square root. For some reason that got, the font on that was a little funky. So this is y equals the square root of x. So I'm not going to choose -2, -1, 0, 1, and 2 for my x values because I cannot take the square root of -2 for number 1. So I can't put a negative value underneath here. The smallest value that I can put under here for x is 0. So if I put 0 in for x, I will get 0 as its square root. The square root of 0 is 0. And so you can think of it this way. I'm going to put the table of values down here that we're using for a lot of these. So the lowest value I can choose for the square root function is 0. If you take the square root of 0, you get 0. The next number after 0, that's a perfect square, would be 1. So the square root of 1 is 1. The next number after 1 is 2. 2 is not a perfect square, so I can't take its square root. That doesn't mean that it doesn't have one, I just can't do it in my head. So you could do it on your calculator, so it's still an included value, it's not excluded in the domain. The next number after 2 is 3. 3 is not a perfect square. The next number is 4. So we're going to put in 4, the square root of 4 is 2. So these points would be 0, 0, 1, 1, and then to the right 4 and up 2. So it's like a little half curve. It goes like this. So here we have a restricted domain. Notice that there is nothing on the left side of this graph. That means there are no negative values for x. Remember, the lowest value we had for x is 0. And so since 0 is an x value of an ordered pair, we are going to start our domain at 0 and include it by using brackets. And then this graph goes forever to the right. It's also going forever up, although slowly, it's forever going up. And that's important to note. That's an infinity sign. So then the range is incidentally the same because your lowest range value is 0. And notice that here's an ordered pair that has a 0 value. And then, so we're going to put brackets at 0. And then range goes low to high, so 0, 2, and then this is going up ever so slowly forever. So it is also positive infinity. All right, let's look at the cube root of x. So here I want to plug in perfect cubes. So something times itself 3 times gives you the number underneath this radical. Anytime you have an odd root, so this index is your root, anytime you have an odd root, you can take an odd root of a negative number. Unlike here where we couldn't take a square root of a negative number, we can't take an odd root. So here is going to be my table of values. So I have my x and y. And I'm going to use my smallest negative perfect cube that I can fit on my graph is going to be -8. Because that's -2 times -2 times -2. If I try to do -3, which is smaller than, I don't know what, yeah, that's what I want is -8. If I try to do -3, that would be -3 times -3 times -3 is -27. I cannot fit -27 as an x value on here. So the cube root of -8 is -2 because that's the number times itself 3 times that gives you -8. The next perfect cube that's bigger than -8 is -1. And the cube root of that is -1 because -1 times -1 times -1 gives you -1. The next perfect cube is 0, so you're going to find out that 1s and 0s are perfect nth roots. So the cube root of 0 is 0 because 0 times 0 times 0 is 0. And then on the positive side, 1 is a perfect cube, so the cube root of 1 is 1. And 8 is a perfect cube, the cube root of 8 is 2. So those are the values we're going to attempt to graph. So this is kind of like a sideways y equals x cubed. So y equals a cube root of x. It looks a little similar, but you're going to notice that it's turned sideways. So if I plot -8, so to the left 8, and then down 2, I'm going to be somewhere around here. And then -1, -1, 0, 0, 1, 1, and then 8, 2. So this graph looks like a sideways S. So there is your cube root of x function. And so this graph goes infinitely to the left and down, and infinitely to the right and down. There's no restriction on this domain. I can put in any number I want to for x, and I can find its cube root. Same thing for the y, because we're going infinitely down and infinitely up. Your range is also -infinity to infinity. Now the next 3 functions, I'm just going to show you what the graphs look like. I'm not going to explain why they are what they are, because we're going to have much more involved units with those. So suffice it to say that the graph of an exponential function typically is going to look like this. And at this point right here is going to be 0, 1, which is going to be an important part of the graph. And then as you can see, the graph goes to the left infinitely, and it goes to the right infinitely. And what's going to happen with this graph is it is not, and in fact, let's go ahead and put on here, you don't know what this is yet, but this is called an asymptote. And this graph will not cross, the parent graph will not cross this asymptote right here. So it's going to go to the left and get closer and closer to a y value of 0, but not actually touch it. So because it goes to the left infinitely, the lowest domain value is -infinity. And because it goes to the right infinitely, the largest domain value is +infinity. Now let's talk about the range. This asymptote represents the bottom portion of the range. The lowest y value will never be 0 because this graph will never touch or cross this asymptote, but it's like a fence. So the smallest y value is going to be 0, but there is no ordered pair on this graph that has a y value of 0. So it's going to be an open function there at 0. So instead of brackets, we're going to put parentheses, meaning you can get as close as possible to 0, but not become 0. Then this graph is going up infinitely. You can see it's going up infinitely. And so the highest y value is +infinity. Then let's talk about what's called a logarithmic function. So the logarithmic function is actually based off of the exponential function, but again, we'll go into this in a lot more detail at a later date. But this essentially is what the logarithmic function is going to look like. And the asymptote on this one is going to go vertically at the y-axis. And so this graph is going to approach an x value of 0 but never ever reach it. So this function actually has the x value restricted. Notice there's no x values over here. And we come to this fence that starts at an x value of 0, and then it is going to go to the right infinitely. So on this one, your domain is going to be an open at 0 because it doesn't include 0, but we will go to +infinity. Now the range, you may note that this is going down forever and it's going up and to the right forever. So down and up are range values, so it's -infinity and +infinity. And what you might notice is that the domain and range on these two functions are reversed. There's a reason for that. It's called an inverse, and we'll get into that at a later date. And also let me note that this point right here is 1, 0, which I will also point out is a reversal of this point here. Notice that the x's and the y's switched. All right, then the final function, so I guess we only did 10 parent functions, is called the reciprocal function. And it means you're going to take 1, and for the parent function, this is going to remain 1, and divide it by an x value. Remember, the only thing that you cannot let x be is 0. So there's going to be this asymptote for this parent function here on the y-axis, and because the only way for this fraction to have a y value of 0 is if the numerator was 0. There's no way you can exchange a constant for 0. This fraction will never, ever, ever have a y value of 0. So you actually have two asymptotes. And again, don't fret. We're going to go over these in much more detail at a later date. And then I'm going to have these things called branches. So it's kind of and that should be a gentle curve. It's not an L shape. It should look more like this. Okay, and so your domain, you have a graph all the way to the left that's going forever, and then this part of the graph's all the way to the right going forever. The only break that you have in the graph is if you're traveling this graph in this direction, you have to hop over this asymptote at 0 and x value of 0 to get to the other side. So your domain is going to go from negative infinity. So we're going from negative infinity. There's a graph below me there. Until I hit 0, that's like an electric fence. We can't touch it, so we have to hop over it. So we come to 0, have to hop over it. So because 0 is not part of the domain, it's an open circle, in this case a parentheses. We're going to union that with, on the other side, we start close to 0. So when we hop that fence, we should start and end with 0 because we hop that fence. And then we're going to go on to positive infinity. So this is your most difficult domain to look at because you've got double asymptotes. The same thing is going to happen with your y. We have this value going down forever. So your lowest y value is negative infinity until you come up to here, this new electric fence right here. We can't touch it, so we're going to hop it. And then we move up forever. And so this is the same range that you're going to get. You're going to go from negative infinity to 0, hop that horizontal fence, and go from 0 to positive infinity. And that's all we're going to talk about with parent functions. On the back of this sheet, or the next slide, we're going to start to look at algebraic equations and look at, and these are going to be parent functions that have been translated, and look to see how that affects the domain and range. So let's recall that the only functions that actually have a restriction on the domain, which is really what our concern is, none of these, right? Only these. The ones that have restrictions on the domains are not the, oops, I did not want to do that. There we go. The ones that have a restriction on the domain are not these ones where it says negative infinity to positive infinity. It's something like this, or this, or this. So these three, a square root, or an exponential, or a logarithmic, which we won't do much with these, or a fraction. You're going to work mostly today with the square root and the fraction. So let's look at the next slide. All right, so we're going to try to identify the domain, only the domain. We're not going to worry about the range, just by looking at the equation. So this is the equation of a linear function. So I want you to get in the habit of thinking, what is the parent function? So the parent function is linear. Linear functions have no restrictions. So the domain for this one is negative infinity to positive infinity. The only things that cause a restriction would be a variable underneath a square root, or an even root for that matter, but you're mostly going to be concerned with the square root, or a variable in a denominator. Those are the only things you have to worry about. Sometimes you're going to have a variable underneath the square root that's in a denominator, and that gets a little crazy. So this one is not one of those situations, so it's unrestricted. This one, however, I don't care about the x plus 1. I care about only the 3x plus 12. So that's the only part right there that I care about. That denominator right there, this whole denominator, it cannot equal 0. So we have to figure out what x value is going to create 0 in that denominator. So we're just going to take that out. Whoops, I don't know why that just moved. We're going to take that out, 3x plus 12, and we're going to set it not equal to 0. So subtract 12, you're going to solve for x, and you get 3x is equal to negative 12, and then divide by 3, and then you get x is equal to negative 4. That is the only value that will cause a restriction on the domain. So your domain can be any value but x equals negative 4. So how does that look? Domain is equal to, you're going to go from negative infinity to negative 4. We're not going to include negative 4. We're going to union that with negative 4 to positive infinity. And that's it. So all this says is you're going from negative infinity to positive infinity, but you're not including negative 4. All right, so let's look at this one. We have a dreaded variable underneath a radical. So your restriction for here, again, I only care about this part right here. That part, because it's underneath a radical, has to be greater than or equal to 0. Because it's underneath a square root, we have to set whatever's underneath there. So in this case, x plus 1, set it greater than or equal to 0, and then solve for x. This one, we just have to simply subtract 1. And x has to be greater than or equal to 0. So our smallest x value, so if you think about this on a number line, if x were greater than or equal to 0, you'd have a closed circle at 0 and an arrow to the right. That means that we're going to start at 0 and go forever to the right. So our domain will be 0 and including 0, and we're going to go to positive infinity. This one over here, I'm just going to quickly sketch the number line on this one, just so you can kind of see what it means. So we have negative 4 here, and then we have what, like negative 2 here and negative 6 here. So you would have an open circle at 4, but an arrow to the right and an arrow to the left. That's what the domain would look like on a number line. Then let's look at 2D. So 2D has something that's bad, and the bad thing is that you have x minus 7 in the denominator. So remember, that cannot equal 0. So we're going to set x minus 7 not equal to 0. So it's going to give us just one value. So this is just like, what was this one above here? Just like 2b. So we're going to add 7 to both sides. And we get x is equal or not equal to 7. So x can be anything but 7. So again, it looks like that number line with an open circle at 7 and an arrow going to the right and the left. So your domain is going to go from negative infinity to 7. We don't include the 7, so we have open parentheses, union, open parentheses 7 to positive infinity. So that's that set notation where it's saying you're basically going from negative infinity to positive infinity, but we're not including 7. All right, here on this one, as you look at it, we have x as a base. That's okay. I can have any value for x there. I can have any value for x there. I don't see an x that's underneath a fraction, in the denominator of a fraction, or underneath a radical. So since that's the case, there's no work to be shown. Your domain is negative infinity to positive infinity. I don't even have to graph it. Now, this one actually has a double restriction. We have in the numerator, normally I don't care about the numerator of a fraction, but this x value here cannot be negative. So remember that x value underneath there has to be greater than, whoops, I don't know what just happened, has to be greater than or equal to 0. So we have two restrictions, we're going to have to combine the two. So for that one, on the number line, it would look like this. Right? And then greater than or equal to 0 would be a closed circle at 0 and an arrow to the right. Then we're going to take this denominator right there. It cannot equal 0. This one was greater than or equal to 0. This one cannot equal 0. So x minus 7 cannot equal 0. To solve for x, you add 7, and you get x cannot equal 7. So as we go along on this number line up here, we get all the way, here's 4. Why do I keep, Like my palm keeps hitting something. So here's like 4, 6, 8. Won't 7 be like in here somewhere? So there's going to be a 7 like right here. We have to have an open circle at that 7, and then the arrow can continue on to the right. So this is kind of a weird, and sometimes it's helpful to draw this number line so you can kind of see what's my leftmost value and what's my rightmost value. So my smallest x value is 0, and it's included. Then I come to 7, I have to skip it. So we're going to have to draw an interval for this, and then an interval for this, and unionize it. So my domain starts and includes 0. And then it goes to this value 7, that's a 7 there. So it goes to 7, we don't include 7, so that's open parentheses, union, and then we have to combine this interval. Well, it starts at 7 and goes to infinity, but it doesn't include 7. So that's probably the weirdest one of all. There's that whole domain. So you're going to practice those. You only have about 10 problems to do for homework, and it's a worksheet attached to Google Classroom. So just make sure you write down your original problem, show all your work, how I've shown on here, and then check your answers on my website. Good luck.